Hello guys, I hope I am audible. Day 2 live machine learning algorithms. Hello, good evening everyone. Agenda 1 is about ridge and lasso regression. Second is assumptions of linear regression. The third point that we are probably going to discuss about is logistic regression. Then the fourth thing that we are going to discuss about is something called as confusion matrix. The fifth thing that we are going to consider about is practicals. So this is the agenda for linear, ridge, lasso, and logistic. So guys, um, I've given the agenda of this particular session. So in this session, we are going to discuss this all things. Please make sure that you hit like, and still we have 2 to 3 minutes, and then probably we will start. Okay. Sumit, this p-value is basically used in OLS method. In stats, you have something called as OLS, ordinary least square. Okay, and in that specific topic, you can basically find out the p-value, and then you can basically check whether the p-value is less than the significance value or not. Okay. I called your office, but no one picked call. Which office did you call? In our office, we don't have phone. Everybody has mobile. Okay. Okay, guys. So we'll wait for another 2 minutes. First of all, how are you all? I hope you are doing well. Yes, I Harsha Reddy. I will update SQL playlist. In a day, I can work on 2 to 3 videos only. I cannot work on 100 videos. So try to understand. Okay. Low voice. Guys, is good. I think everybody is able to hear me out. Practicals, guys. Fifth point. I am able to hear myself well. So I think you should also be here to hear me, right? Sumit, by OLS also you can do linear regression. Guys, is my voice low? No, right? Fifth point is practicals. Practicals implementation. My God. Again, I will write it for you. So, fifth point is basically practicals. Practical implementation. Okay. Guys, I cannot increase more than this. It is already in the increased manner. It is 100% from my side. So there may be some problems either with your phone or from whichever device you are actually connected in. Okay. Okay. So let's go ahead and let's discuss about ridge and lasso regression. So here, don't spam. Again, I'm telling you, whoever is spamming, I will remove them. Okay. I don't want to waste my energy in that. So first topic that we are probably going to discuss is something called as ridge and lasso regression. So let's understand about ridge and lasso regression. If you remember in our previous session, what all things we discussed? In the previous session, guys, whoever had attended, hit like first of all. Now, in the previous session, whatever things we have discussed, just tell me what all things we have actually discussed in our previous session. Guys, in the previous session, what all things we have actually done? So, whoever had attended, please tell me. So, in our previous session, we have discussed about linear regression, and then we had discussed about the cost function. We have discussed it about r square adjusted r square, sorry, r square and adjusted r square. We have discussed about it. Gradient descent, we had discussed about it. So tell me, what was the cost function that we discussed? The cost function of linear regression, whatever things we have discussed, what it was? It was nothing but 1 by 2m summation of I is equal to 1 to m h theta of x I minus y I whole square. So this is the cost function that we had discussed, right, yesterday. And this cost function was able to give us a gradient descent with respect to the j of theta 0 or theta naught. So I can also write this as j of theta comma theta 0 comma theta 1, right? So we have already discussed this. Now let's go to the next step. Okay, now let me give you a scenario. Let's say that I have a scenario over here and I have this specific scenario. Okay, let's say that I just have 2 points which looks like this. Okay, now if I have these two specific points, what will happen? I will probably try to create a best fit line. The best fit line will definitely pass through all the points like this, right? It will definitely pass through all the points. So if I try to calculate the cost function, what will be the value of j of theta 0 comma theta 1? Let's say that in this particular case, since it is passing through the origin, my theta 0 will be 0. Okay, so what will be the value of theta 0 comma theta 1? Tell me, what will be the value of theta 0 comma theta 1? Please keep on hitting like, guys. Congratulations, Bawali Coder, he got an internship. So what will be the value of theta 0 comma theta 1? So here obviously you can see that there is no difference, so it will obviously become 0. Now understand this data that you see, right? This data is basically called as training data. Okay, so this data that I have actually plotted with 2 points, these are specifically called as training data. Okay, specifically called as training data. Now, what is the problem in this data right now? See, right now, exactly whatever line is basically getting created over here, which is through the hypothesis, over here you can see that it is passing through every point. So that is the reason your cost is 0. And our main aim is to basically minimize the cost function. That is absolutely fine. Now, in this particular case, in which my model, if this model is getting trained, initially this data is basically called as training data. Now, just imagine that tomorrow new data points comes, right? So if my new data points are here, let's consider that I want to basically come up with this new data point, right? New data point over here. Now in this particular scenario, if I want to predict with respect to this particular point, let's say my predicted point is here. Is this the difference between the predicted and the real point quite huge? Yes or no? So this is basically creating a condition which is called as overfitting. That basically means even though my model has given or trained well with the training data, or let me write it down properly over here. So this condition, since you can see that over here, my each and every point is basically passing through the best fit line. Okay. So because of that, what happens? It causes something called as overfitting. So you really need to understand what is overfitting. Now, what does overfitting mean? Overfitting basically means my model performs well with training data, with training data, but it fails to perform well. It fails to perform well with test data. Okay, now what is the test data over here? The test data is basically this points. The real test data answer was this points. But because my line is like this, I'm actually getting the predicted point over here. So this distance, if I try to calculate, it is quite huge, right? So in this scenario, whenever I say my model performs well with training data, it is basic when the model performs well with training data and it fails to perform well with test data, then this scenario we say it as overfitting. Okay, overfitting. So this scenario, when the model performs well with training data, I have a condition which is called as low bias. Okay, and when it fails to perform with the test data, then it is basically called as high variance. Very important. Okay, I will make each and everyone understand one by one. If it is performing well with the training data, that is basically low bias, and whenever it performs well with the fails to perform well with the test data, then it is basically high variance. Okay, now similarly I may have another scenario which is called as underfitting. So let's say that I have something called as underfitting. Now in this underfitting, what is the scenario? The model fails to perform, it gives bad accuracy. I'll say that model, okay. Always remember, whenever I talk about bias, then you can understand that it is something related to the training data. Whenever I talk about test data, at that point of time, you talk about variance. And that specifically, whenever you talk about variance, that basically means we are talking about the test data. Okay. So for an overfitting, you will basically have low bias and high variance. Low bias with respect to the training data and high variance with respect to the test data. Okay. Now, if the model accuracy is bad with training data and the model accuracy is also bad, it is also bad with test data, is also bad with test data. In this scenario, we basically say it as underfitting. So these are the two conditions that are with respect to underfitting. That basically means that both for the training data also the model is giving bad accuracy, okay, and again for the test data also it is basically having a bad accuracy. So in this particular scenario, we can definitely say two things out of underfitting. One is high bias and high variance. Okay, so this is the condition with respect to underfitting. Very super important. Okay, high bias and high variance. No, Rohit, I think it is same. Low bias? No, not low bias. Underfitting basically means it is high bias and high variance. Okay, it is giving bad accuracy, right? See, bad accuracy with respect to training data also and with respect to test data also. High bias and low variance is overfitting. No, but the model performs well with the training data, right? Yes, model performs well with the training data. So because of that, it is low bias. Okay. It fails to perform well with the test data. So it is basically high variance. The error rate will be high. Okay. Let me just explain you once again. Suppose let's consider I have one model. I have model 2. This is model 1. Okay. This is model 1. This is model 2. and this is model 3. Okay. Low bias and high variance. High bias and low variance. Okay, let me verify once again. I'll just search the research paper. Okay. Low bias and high variances overfitting. I really need to verify with the research paper now. Okay. Let me confirm this probably till tomorrow session. Okay. If you are basically having overfitting, high variance and low bias. No, no, no. Okay. Fine. Low again. Please try to understand whatever I'm teaching. Please focus on that. Okay. Okay, guys. So suppose let's say that I have my model. My training accuracy is, let's say that my training accuracy, my error rate, or I'll say my training accuracy is, let's say 90%, and my test accuracy is, yes, I'm saying it right. Many people are simply pinpointing. So let's say that my test accuracy is 80%. Okay. Now in this particular case, let's say that my training accuracy is 92% and my test accuracy is 91%. Okay. And let's say my model 3 is basically having training accuracy as, okay, um, if my training accuracy is somewhere around, let's say my training accuracy is 70% and my test accuracy is 65%. Now tell me which scenario is overfitting, which scenario is underfitting. So if I take this particular case, it is basically overfitting. Okay. If I take this particular thing, this basically becomes my generalized model, my generalized model. And when I talk about this is my, I'll just say that, okay, I'll also put nice colors so that you will be able to understand this. This becomes our generalized model. Okay. And this finally becomes our underfitting, right? Underfitting. So here is my red color. I will just say it as underfitting. Okay. So what are the main properties of this? Overfitting, as I said, in this scenario, okay, since it is performing well with the training data, so it will be low bias, high variance. Okay. In this particular case, it will be low bias, low variance. In this particular case, it will be high bias and high variance. Understand in this terminology, in this particular way, you will be able to understand. So why do we require always a generalized model? Because whenever our new data will definitely come, generalized model will be able to give us very good output. Okay. So let's go back to this particular example. Here you will be able to see this straight line, the red line that I have actually created is basically overfitting. Okay. So that whenever I probably get the new points, which is having this real value and the predicted points, here you'll be able to see the difference is quite huge. So because of this, it will definitely be a scenario of overfitting. where it has low bias and high variance. Okay, so I hope you have understood this. So again, let me go ahead and take this example. So this was my line which I have actually drawn. I had 2 points, and when I draw this line, which was a best fit line to which is passing through both the points, this scenario is basically causing a overfitting problem. Overfitting problem. And I have also shown you my j of theta 1 will be 0 in this scenario, since it is passing exactly and the predicted point is also over there. Okay, so now understand one thing is that what can we take out from this? What assumptions we can take out from this? Definitely, if I talk about our cost function here is nothing but 1 by 2m summation of I is equal to 1 to m, okay, h theta of x of I minus y of I whole square. Now let's consider that I am going to use this h theta x and I'm going to basically write it as y hat. Okay, let's focus on this specific point. Okay, so when I take this, I'm just going to focus on this particular point. So here I will definitely write it as y hat minus y of I whole square. Okay, so this is my y hat of I minus y hat yi whole square. So this is nothing but the difference between the predicted value and the real value. Okay, this is what I'm actually trying to get. Now in this scenario, if I am adding these values, obviously I'm going to get the value as 0. Now I have to make sure that this value does not come to 0 because this is still overfitting. So that is where your ridge regression will come into picture. Ridge and lasso will come into picture. Now when I use ridge and lasso, suppose if I use ridge, okay, now in ridge, what we say this is also called as L2 regularization. We also call it as L2 regularization. Now L2 regularization, what it does is that it basically adds a unique parameter or add a one more sample value, which is like lambda multiplied by slope square. Now what is this slope? Whatever slope of this particular line it is, we are just going to square it off. Now suppose if I take my equation which looks like this, h theta of x is equal to theta 0 plus theta 1 x. Now in this particular case my theta 0 was 0. So my h theta of x is nothing but theta 1. What is theta 1? This is specifically called as slope. And I am basically taking this theta 1, I'm actually making it as a square. Okay. So always understand, I don't want to make this as 0 because if it becomes 0, it may lead to overfitting condition. Now what will happen if I add this particular equation? If I add this particular equation, this will obviously come as 0. Let's consider my lambda value over here. My lambda value is 1. I'll talk about how do you set up lambda value. Okay, let's consider that I'm initializing it to 1. Let's say my lambda value is 1 over here. Okay, my lambda value is basically 1 over here. Now, what I will do is that this lambda value is 1. Let's consider our slope value initially is 2. Okay, let's consider. Okay, my slope that is theta 1, I'm initializing to 2. Let's consider it. Okay, and because of this 2, I got this best fit line. I'm just going to consider it. So if I do the total sum over here, if I'm just considering this value is 3. Now the cost function will not stop over here because still it has to minimize. It has to reduce this 3 value. So what it will do? It will again change the theta 1 value, and let's say that my theta 1 value has changed. Now it got another best fit line which looks something like this. Okay, which looks something like this. This is my next best fit line. Okay, I'll talk about lambda. Lambda is a hyperparameter, guys. What exactly is lambda? I'll just talk about it. Okay, just give me some time. Okay, now when I basically change this line, now see why I'm getting this line. Let's consider I have changed my theta 1 value. Since we need to minimize, now when we need to minimize, what it will do, we'll again calculate the slope of this particular line, and then we will try to create a new line. Now when we, sorry, it is 2, not 3. Okay, let's say that this is 2. Yeah, 2, 2, 2, 2, 2. I will try to minimize this 2. Okay. Now, slope square. Just a second, guys. 0 plus 1 multiplied by 2 square, which is nothing but 4. So now my cost function will not stop over here. Okay, my cost function will not stop over here. Okay, so we are going to still reduce this. Okay, we are going to still reduce this. Now, in order to reduce this, again, theta 1 value will get changed, and then we will get a next best fit line for this point. Now, what will happen in this scenario once we have this best fit line? We will definitely get a kind of small difference, right? With respect to the real point, we'll get some kind of difference. So now, if I go ahead and consider the new equation, my y hat I minus yi whole square plus lambda of slope square, this value will be a small value now because I have some difference. This value will definitely be a small value, okay, because I have difference over here, right? I have some difference over here, so this will be some kind of value, and then plus again 1 multiplied by, now understand whether the slope will increase in this particular case or whether it will decrease in this particular case. There will be some slope value. Let's say that I have got some slope of this particular line, right? In this particular scenario, again your slope will definitely decrease. So let's say in the case of 2 initially it was, now it is basically 1.36 whole square. Now this small value plus 1 plus 1.3 square, or let me consider that my slope is now one simple value, that is 5. Okay, so if I get this, it is 2.25. 2.25 plus small value, it will be less than 3 only, right? Right, it will be less than 3. Understand this thing. It will obviously be less than 3 or equal to 3. But understand what is happening. The value is getting reduced from 4 to 3. Right? So this is the importance of ridge. Now what will happen is that you will try to get a generalized model which has low bias and low variance instead of this overfitting condition. Okay, so I hope everybody is able to understand this. Okay, I hope everybody is able to get this particular thing. You know why specifically we are adding ridge L2 regularization. It is basically to prevent overfitting, because here you are not stopping here. You are trying to reduce it unless and until you get a line. You get a line which will be able to handle as a generalized model. Okay, now here you can see, now if I have my new points like how I drew over here, now the distance will be less, right? So now you will be able to see that it will be able to create a generalized model. Okay, I hope everybody is able to understand. Guys, this will be a small value only. See, initially when we have this line, obviously we have 0. If we try to slightly move here and there, Muhammad Hasir, I will remove you, I'm telling you again. Okay, so here you will be able to see that it will just a slight movement. But what this movement is basically specifying, it is specifying that the slope should not be steep. Should not be steep. If we probably have a steep slope, it obviously leads to most of the time overfitting condition. Okay, it should not be steep. It should be it should be less steeper, but it should actually help you to create a generalized model. Okay, so you will be seeing that after playing for some amount of time, this value will not reduce after some point of time. It will get almost, it will be a minimal value, it will be a smaller value. Okay, and for this also you have to specify iterations, how many times you probably have to train them. Now this iterations is also a hyperparameter. Based on number of iterations, you will probably see your R square or adjusted R square over here, right? So this iterations, based on the number of iterations, it will never become 0, guys. Understand? Because 0, it is not possible. If it becomes 0, trust me, it is an overfitting model. You cannot get that is something 0 over here. Now what is lambda? Coming to this lambda is a hyperparameter. This is basically to check how fast you want to lessen the steepness, or how fast you want to make a steepness grow higher, right? And this lambda will also be selected by using hyperparameter, and this also I'll show you today in practical. Okay, what do you mean by iterations? Iteration basically means how many times I want to change the theta 1 value. Yesterday only I showed you, right? How many times you want to change the theta value? That is the convergence algorithm, right? This we have discussed yesterday. Convergence algorithm, right? So is it clear, guys, with respect to ridge or L2 regularization? Understand, over here L2 regularization or ridge is basically used in such a way that you should never overfit. Okay, I hope everybody is able to understand it clearly. Can I get a quick yes if you are able to understand? Why we assume theta 0 is equal to 0? Because I am considering that it passes through a origin, right? Origin over here. Lambda is a hyperparameter. Okay. Yes, we get by cross validation. I'll show you that. Steep basically means how steep the line is. If I have this line is quite steep. If I have this line, this is less steep, right? Are you able to understand, guys? I hope everybody has understood about this all parameters that we have discussed about overfitting, underfitting, very important interview question. Can I get more number of likes because 1,000 people are there? Please try to hit likes, and definitely, yes, it will penalize. Yes. Okay. Now everything is fine. See, everything is fine. Now, if I go to the next regularization, which is called as Lasso, Lasso regression, this is also called as L1 regularization. Now, here the formula will be changing little bit. Okay, here the formula will be changing little bit. Now, what is the formula over here? Here you will be having y hat of minus of y whole square. Here you will be adding a parameter lambda, but understand, here you will not be adding slope square. No, here you will be adding mode of slope. Here you will be adding mode of slope. Sorry, mode of slope. Okay, here you will be adding mode of slope. And this mode of slope work is that it will actually help you to do feature selection. Now you may be thinking, how feature selection, Krish? Okay, let's consider an equation over here. Let's say that I have many features. I have many features. Okay, so my h theta of x, which I'm indicating here as y hat, let's say that I'm writing this equation. Okay, apart from preventing for overfitting, it will also help you to do feature selection here. Let me just show you over here with an example. This h theta of x, which I'm probably writing as y hat, this will basically be indicated by something. Over here you'll be able to see that it is nothing but, let's say that I have multiple features like this. Multiple features like this. Multiple features like this. Like this, I have a lot of features. Okay. Now in this particular features, obviously there are so many coefficients over here, so many slopes over here. Now mod of slope will be what? It will be nothing but mod of x1 plus x2 plus x3 plus x4 plus x5 like this up to xn. Right? Now in this particular case, how it is basically helping you to, sorry, not x1, sorry, just a second. Just a second. This mod of, I have taken the data points. This is not data points. This should be your mod of theta 0 plus theta 1 plus theta 2 plus theta 3 plus theta 4 plus theta 5 like this up to theta n. Okay. So here you will be able to see that this is how I will basically be calculating the slope. Now, as we go ahead, guys, whichever features are probably not playing an amazing role, the theta value, the coefficient value, the slope value will be very, very small. It is just like that entire feature is neglected. You know, that entire feature is neglected. Now, in this particular case, we were doing squaring over here. Because of this squaring, that value was also increasing, right? But here, because of the mode, that value will not increase. Instead, it will be a condition wherein we are basically neglecting those features that are not at all important in this specific problem statement. So, with the help of L1 regularization, that is Lasso, you are able to do two important things. One is preventing overfitting, preventing overfitting. And the second case is that if you have many features and many of the features are not that important, okay, in basically finding out your slope or your line or the best fit line, in that particular case, it will also help you to perform feature selection. So this is the importance of the entire. What is the importance of this? This is the importance of the ridge and the lasso regression that we are doing. Here I'm just going to write L1 regularization, and obviously we have discussed about L2 regularization also. Okay. Now you have probably understood lambda is one hyperparameter, okay, which we will specifically using, okay, and based on this lambda, this will be found out through cross validation. Cross validation is a technique wherein we will try to probably train our model and try to find out this specific things, okay, what should be the exact value, and there also we play with multiple values, okay. Overfitting, not underfitting, overfitting. It prevents overfitting, Ankur. Okay. Okay, guys. Clear, everybody? I have a lot of things to cover. Please let me know whether you are clear or not. In short, what we are doing, we are just trying to reduce the cost function in such a way that it will definitely never become zero, but it will basically reduce based on the lambda and the slope value. Okay. I hope everybody is understood. Why theta 0? These questions, I guys, see, if you have not attended the yesterday's class, then it will be difficult to understand. Okay. In most of the scenario, if you ask me, we should definitely try both the regularization and see that wherever the performance matrix is good, we should use that. Okay. Arey bhai aayega. What is cross validation? I'll discuss about it. Don't worry, no. But what is cross validation basically means, I will try to use different lambda value and basically use it. So in a short, let me write it down again. For ridge regression, which is an L2 norm, okay, here I'm simply writing my cost function in this particular case will be little bit different. Here I can definitely write my cost function as h theta x of I minus y of I whole square, okay, plus lambda multiplied by slope square. What is the purpose of this? The purpose is very simple. Here we are preventing overfitting. Preventing overfitting. This is the main thing in this. Okay. This was with respect to the ridge regression, that is L2 norm. Okay. Now if I go ahead and discuss about the next one, which is called as lasso regression, which is also called as L1 regularization. In the case of lasso regression, your cost function will be h theta of x of I minus y of I whole square plus lambda multiplied by mode of slope. Okay. So here you have this specific thing. And what is the purpose? What is the purpose? The purpose are two. One is prevent overfitting, and the second one is something called as feature selection. So these two are the outcomes of the entire thing. So please explain how lasso regression atomic. That only I told. No. See, with respect to this lasso, right? You have slopes. Slopes here you will be having theta 0 plus theta 1 plus theta 2 plus theta 3, like this up to theta n. Now, when you will have this many number of thetas, when you have many number of features. And when you have many number of features, that basically means you'll have multiple slopes, right? Those features that are not performing well or that has no contribution in finding out your output, that coefficient value will be almost nil, right? It will be very much near to zero. In short, you are neglecting that value by using modulus. You're not squaring them up. You're not increasing those values, right? I hope everybody is able to understand. Now, this was the entire purpose of the ridge and the lasso regression, which I have probably taken up this much time. Now, I will continue, and probably I will also discuss about the assumption of linear regressions. Assumptions of linear regression. Okay, so what are the assumptions of linear regression in this particular scenario? So assumption is that, number one point, linear regression, if our features are in normal or Gaussian distribution, if our features follows this particular distribution, it is obviously good. Our model will get trained well. So there is one concept which is called as feature transformation. Okay. Now in feature transformation, always understand what will happen if a model does not follow a Gaussian distribution. Then we apply some kind of mathematical equation onto the data and try to convert them into normal or Gaussian distribution. The second assumption that I would definitely like to make is that standard scalar or standardization. What is standardization? Standardization is a just one someone tell me what is standardization, right? What is standardization? What is standardization? This is a very much important point. Aditya, it is not necessary, and that only I'm telling, right? If your data is not Gaussian or normally distributed, we try to check that whether this data can be converted into a normal or Gaussian distributed, right? Standardization is nothing but it is a kind of scaling your data, okay, by using z-score. I hope everybody remembers z-score. This is what we basically apply, okay. There your mean is equal to 0 and standard deviation equal to 1. Why do you perform this? Can anybody tell me? See guys, wherever you have gradient descent involved, right, it is good to basically do standardization, because if our initial point is a small point somewhere here, then to reach the global minima or training will happen quickly. Otherwise, what will happen if your values are quite huge, then your graph may be very big and the point can come over there. Okay. And the third point is that this linear regression works with respect to linearity. It works if your data is linearly separable. I'll not say linearly separable, but this linearity will come into picture. If your data is too much linear, it will obviously be able to give a very good answer. Like logistic regression also, which we are going to discuss today, this also has the same property. Okay. Now you may be asking, is it compulsory to do standardization? Guys, if you want to increase the training time of your model, or if you want to optimize your model, I would suggest go ahead and do standardization. Okay. Now coming to the fourth point, here you really need to check about multicollinearity. This is also one kind of check we basically do. What is multicollinearity? Let's say I have x1, I have x2, and this is my output feature. I have, let's say, x3 also. Okay. Now let's say that if I try to see the collinearity of this two feature, how correlated these two feature are. Let's say that these two feature are 95% correlated. Is it a wise decision to use both the features? And let's say that these two features are 95% correlated, but it is highly correlated with y, right? Let's say this, okay? So is it necessary that we should use both the feature in this particular scenario? The answer should be no. We can drop this particular feature. Okay, we can drop this particular feature. Any one of the feature we can definitely drop it. Okay, and based on that I can just use one single feature and basically we do the prediction. Okay, there is also a concept which is called as variation inflation factor. Variation inflation factor, I will try to make a dedicated video about this. If I try to explain, this will probably take 1 hour. Okay, multicollinearity is also solved with the help of variation inflation factor. Okay, okay, so one more term is there, homosoidacity. Okay, so that kind of terminology is also we use one more condition in this. But if you are almost satisfied with this assumptions, you will definitely be able to outperform in linear regression. Okay, so I hope everybody is able to understand. So VIF, I'll try to create a separate video for it. Okay, so we'll focus on completing the remaining part. Okay, okay, one thing, when I'll do the practical, I'll also show you some of things. Okay, so you have got an idea of the assumptions, you have also got an idea of multiple things. Okay, now let's go towards something called as logistic regression. Hit like, guys, if you are liking the video. Okay, now logistic regression. What logistic regression is, the first type of algorithm that we are going to learn in classification. Okay, let's say that in classification I have one example. Suppose I have, say, number of hours, study hours, and number of play hours. Based on this, I want to predict whether a child is passing or failing. Okay, suppose these two are my features. I want to predict whether it is pass or fail. So here you'll be able to see that I have some fixed number of categories. Specifically in this particular scenario, I have two categories. Binary logistic regression works very well with binary classification. Now the question comes that can we solve multi-class classification using logistic? The answer is simply yes, you can definitely do it. Okay, and that also I'll be discussing as we go ahead. Okay, so let's go ahead and let's try to discuss about logistic regression. Now, what is the main purpose of the logistic regression? First of all, let's understand one scenario. Okay, suppose I have a feature. Let's say I have a feature. Okay, which basically says mm, 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 mhm, number of study hours. Okay, and this is like 1, 2, 3, 4, 5, 6, 7, and let's say that I have pass. This point is basically pass, and this point is basically fail. So I have these two conditions. These are my outcomes. Okay, now what I'll do, I will just try to make some data points. Let's say that if I study less than 3 hours, I will probably be fail. If I study more than 3 hours, then probably I will pass. Say this, I'll make it as fail, and this I will make it as pass. Okay, so I will be having points over here after this. 1, 2, 3. Let's say that this is my training data set. Now the first question says that, okay, Krish, fine, you have some data over here. Whenever it is less than 3, you are basically, the person is failing. If it is greater than 5, greater than 3, it is basically showing data points with respect to pass. Now, can't we solve this problem first with linear regression? Can we solve this problem with linear regression? That is the question. Okay. Can we solve this with the help of linear regression? Now, with the help of linear regression, here the first point will be that yes, I can definitely draw a best fit line. My best fit line in this particular scenario may be something like this. It may look something like this. Okay. So here fail is nothing but 0, pass is 1. The middle point is basically 0.5. Okay. So obviously with the help of linear regression, I'm able to create this best fit line. And I'll put a scenario that whenever the value is less than point, zero point 0.5, whenever the value is less than 0.5, whenever the output is less than 0.5, let's say that my new output is this. I will go and let's say that my new data point is this. Let's say that my new data point is this. And based on this, I will try to do the prediction. I'm actually able to get the output over here. I'm able to get the output over here. Now, when I'm getting the output over here, this basically is 0.25, right? 0.25, right? Now, in this particular scenario, obviously, I'm able to say that, yes, the person, I'll write a condition over here saying that if my h theta of x value is less than 0.5, then my output should be 0. Let's say less than 0.5, I'll say not less than or equal to, less than 0.5, then my output will be 0, right? So in this particular case, 0 basically means fail, right? Similarly, I'll have a scenario where I'll say that if my h of theta of x is greater than or equal to 5, then this will basically be 1, which is nothing but pass. Okay. So this two condition I can definitely write over here. This is my center point. So that any point that will probably come over here, let's say that this point is coming over here, right? Let's say new data point is somewhere coming over here with this red point. Now what I'll do, I will basically draw a straight line. It will come over here. I will just extend this line long. I will extend this line over here, and I will extend this line over here. And here you can see that based on this, I'm actually getting this particular prediction, which is greater than 0.5. So I will say that, okay, the person has passed. Obviously, this is fine. This is obviously working better. Okay. This is obviously working better. So what is the problem? Why we are not using linear regression? Okay. Why we are not using linear regression? Okay. In order to solve this particular problem, why you are specifically having logistic regression? The answer is very much simple, guys. The answer is that whenever, let's say that if I have an outlier which looks something like this, suppose I have an outlier which comes like this over here. What is this value? Let's say that this value is nothing but 7, 8, 7, 8, 9, 10. Let's say that the number of study hours when I'm studying for 9, it is obviously pass. Now in this particular scenario, when I have an outlier, this entire line will change. Now I will probably get my line which looks something like this. Okay, my line will basically move something like this, right? It will now get moved something like this, right? Now when it gets moves completely like this, now for even 5 or even at any point that I am actually predicting, let's say that at this particular point, if I try to find out, it'll be showing less than 0.5. So here this particular value or answer will be wrong, right? Because if we are studying more than 5 hours, obviously based on the previous line, the person had to pass. But in this scenario, it is failing. It is coming less than 0.5. But the real value for this is basically passed, right? So I hope you are understanding. Because of the outlier, the entire line is getting changed. So how do we fix this particular problem? Now in this, two scenarios are there. First of all, obviously because of just an outlier, your entire line is getting shifted here and there. The second point is that over here, sometimes you're also getting greater than 1. You're also getting less than 1. Suppose if I try to calculate for this particular point, if I project it in behind, I will be getting some negative value, right? So this is also one problem, right? So we have to squash this function. If I squash this function, then it will become a plane line, right? How do we squash it? And for this, we use something called as sigmoid activation function or sigmoid function, right? So if somebody asks you, why don't you use linear regression in order to solve this classification problem? Then your answer should be very much simple. You should say these two specific points. Okay. So we will try to go ahead and solve some linear regression now with the help of cost function, everything as such. And we'll try to understand how the cost function will look for logistic regression. Okay. Everybody clear till here? Second reason I told you, right? It is greater than 0. Over here, the line is going greater than 0, right? Greater than 0. I have only 0 and 1, and it is becoming greater than 0. But I have already told that our maximum and minimum value are 1 and 0. Okay? Clear, everybody? So if you are able to understand till here, please hit like and support. I should definitely see a lot of likes. Then only I'll get my Red Bull, right? Energy, basically. Okay? So I hope you have understood why linear regression cannot be used. Okay, I showed you all the scenarios why linear regression should not be used. Now we'll continue and probably discuss about the other things over here. And we will now try to understand fine what exactly logistic regression is all about and how the decision boundary is basically created. Now we'll go ahead and discuss about that specific thing. So let's go ahead. Our values should be always between 0 to 1 over here in this particular case because it is a binary classification problem. Only this should be the answer. Okay. So let's go ahead and let's define our decision boundary. So my decision boundary in the case of logistic regression. First of all, as usual, in logistic regression, we defined our hypothesis. Okay, guys. First of all, let's see. If I'm writing my h of theta, my h theta of x as theta 0 plus theta 1 into x plus theta 2 into x, like this, x1, x2 plus theta n into xn. Now in this scenario, can I write this entire equation as theta transpose x? Yes? Yes or no? Obviously, I can definitely write this way, right? And this is what is the notation that you will probably seeing in many places. Okay? So, with respect to the decision boundary of logistic regression, our theta, see, like this we can write, I'm saying, okay? But since we have to consider two things, one is squashing the line, okay? How that squashing will basically happen? See, if I have this line, we saw in the above, right? If I have this line, okay, this line, let me draw it again. My handwriting is always bad. Suppose I have some data points over here, okay, and I have some data points over here. So if I want to create the best fit line, how will I create? I will basically create like this. But I have to also do two things. One is squash over here and squash over here, right? Squash over here and squash over here. Now, in order to squash, I'm saying squash. Squash means सीधा कर दो, ठीक है? सीधा कर दो. Now, in order to do this, I use a function which is called a sigmoid activation function. That basically means what happens. Obviously, you know this line is basically denoted by h theta of x is equal to, how do you denote this straight line? Let me write it down nicely for you. So how do you denote this straight line? This straight line is obviously denoted by theta 0 plus theta 1 multiplied by x1, let's say. Okay. Now on top of this, I have to apply something. On top of this value, I have to apply something so that I can able to make this squash. I'll be able to make this line straight instead of just expanding in this way. So my hypothesis will basically be now, G is basically a function on theta 0 and theta 1 multiplied by x1. Okay, so here I'm trying to basically, what I'm trying to do, I will apply a mathematical formula on top of this linear regression to squash this line. Okay, to squash this line. So now let's go ahead and let's try to find out what is this G. Okay, what is this G? I will say let z is equal to theta 0 plus theta 1 multiplied by x. I'm just initializing this. Now my h theta of x is nothing but g of z. Okay. Now we need to understand what is this g of z. Okay, what is this g of z and how do we basically specify what is this g function? Okay, so my g function is nothing but h theta of x is equal to 1 by 1 plus e to the power of minus z, which in short, if I try to initialize z now, it is 1 to the power of e to the power of minus theta 0 plus theta 1 multiplied by x. Okay, so this is what is my h theta of x, which is my hypothesis. And this obviously works well because it is being able to squash the function. Okay, it is able to squash the function. Okay, I hope everybody is able to understand. So this is basically my hypothesis, which I am definitely trying to use it. Now this is my hypothesis. And this function that you are actually able to see is called as sigmoid or logistic function. Okay, sigmoid and logistic function. Now you need to understand what does this sigmoid function look like in graph. Okay, in graph it looks something like this. Okay, so this is my z value and this is my, okay, this is my g of z. Okay, this is my 0.5. Okay, your sigmoid function will have this curve. So this is your 1, this is 0. Your value, when now from this we can make a lot of assumptions. What are the assumptions that we can basically make? Your g of z, your g of z is greater than or equal to 0.5, is obviously greater than or equal to 0.5 when your z value is greater than or equal to 0. Right? This is the major assumptions that we can basically make. That is, whenever your g of z is greater than your g of z is greater than or equal to 0.5, whenever your z is greater than or equal to 0. Okay, so obviously whenever your z value is greater than 0, it is greater than 0.5. If your z value is less than 0, what it will become? It will basically be less than 0.5. So you can write that specific condition also you want. Okay, so this is the most important condition over here, right? Now still the question many people are saying why it is called as logistic regression. See guys, with the help of regression you are creating this straight line, and with the help of the concept of sigmoid you are able to squash it. So they have probably combined that name and basically have written in this way. Okay, so let's go ahead. I hope everybody has got till here. I'm loving it. See, I'm teaching the entire maths, which probably I've also not taught in my previous videos. Okay, will squashing of the best fit line help to overcome the outlier issues? Yes, obviously it will be able to help you. I hope you are able to understand, because this way in my previous video also I have not explained. Okay, okay, so let's go ahead and let's try to solve the problem statement. Now usually let's consider my training set. Let's consider my training set. Suppose I have some training points like this: x of 1 comma y of 1, let's say x of 2 comma y of 2, okay, x of 3 comma y of 3. Like this I have a lot of training points, and finally x of n comma y of n. Let's say that this is my training data. Okay, so here my y will belong to what? 0 or 1, because I will only have two outputs, right? Since we are solving a binary classification problem. Okay. So here is my training set with two outputs. And I hope everybody knows about j theta of z. It is nothing but 1 plus e to the power of minus z. Here your z is nothing but, what is z? What is z? Theta 0 plus theta 1 multiplied by x1. Okay. Okay. So this is your theta 0. Now what we have to do, we have to select this theta. Now in this particular case, let's consider that my theta 0 is 0 because it is passing through the origin. Okay. Just for time pass sake. Okay, suppose my z is theta 1 into x. So now I need to change, what is my parameter? My parameter is theta 1. I have to change parameter theta 1 in such a way that I get the best fit line, and along that I apply this sigmoid activation function. Okay, so all these things are basically there. Now let's go ahead and let's first of all define our cost function, because for this we definitely require a cost function. Now, everything will be same. Obviously, you know the cost function of linear regression because the first best fit line that you are probably creating is with the help of linear regression. Now, in this particular case, in the case of linear regression, just tell me what is the cost function. So here you can basically write j of theta 1 is nothing but 1 by 1 by m summation of I is equal to 1 to m 1 by 2, and here you have h theta of x minus y of I whole square, right? So this is your entire thing, right? Of, if you remember linear regression, whatever things we have discussed yesterday. Okay, so this is the cost function. Okay, let's consider that for linear regression, for this is for the linear regression. Now for the logistic regression, what will happen? For your logistic regression, I will take the same cost function h theta of x. Now you know what is h theta of x? It is nothing but 1 plus e to the power of minus theta 0 plus theta 1 multiplied by x, right? This is my, with respect to logistic regression, this is my entire equation, right? Right? Now, similarly, I will try to only put this h theta of x. Let's consider that this is my cost function. This is my cost function. Only my h theta of x is changing in this particular case. So if I go ahead and write my cost function, I can basically say 1 by 2 h theta of x of I minus y of I whole square. And in this particular scenario, what is h theta of x? It is nothing but 1 plus e to the power of minus theta 1 x, right? So this is what this is getting replaced, and this is my logistic regression cost function. I'm just considering this cost function part, this part. Later on, if you replace this to this, see, if I replace this to this, and if I replace this to this, it becomes a logistic regression cost function. Okay. Intercept, I'm considering it as 0, guys. Okay. Intercept, I'm just considering it as 0 for time's sake right now. Okay. Now, when I'm replacing this to this, then it becomes a logistic regression cost function. But there is one problem. We cannot use, let's say, I'm just saying that we cannot use this cost function. There is a reason for this. Why we cannot use this cost function for logistic? Because this equation that you are seeing, 1 divided by 1 plus e to the power of minus theta 1 multiplied by x, right? This is a non-convex function. Now you may be considering what is a non-convex function. So let me write it down. So here, this terminology, right? It is a non-convex function. Now what is this non-convex function? Let me show you. And let me differentiate it with convex function. Okay, we'll try to understand what is the difference between non-convex function and convex function. This is related to gradient descent. Very important. This is related to gradient descent. Okay, this is also related to gradient descent. If you remember, with the help of linear regression, whatever gradient descent we are actually getting, with the help of linear regression, whatever gradient descent we are actually getting, it is a convex function like this. This is the convex function which looks like a parabola curve. Okay, parabola curve. Because of this parabola curve, whenever we use this linear regression cost function, specifically because here my h theta of x is what? It is nothing but theta 0 plus theta 1 into x. Because of this equation will always give you a parabola curve. This kind of cost function or convex function you can say. But here your h theta of x is changing. So in the case of, if I use that cost function, you will be getting some curves which looks like this. Okay. Now what is the problem with this curve? Here you have lot of local minima. If local minima is there, you will never reach this global minima. Okay. So that is the reason we cannot use that cost function. Okay. Now mathematically you can also go and probably search in the Google what is the what is the graph or what is the convex or non-convex function. But always remember, whenever we updates theta 1 with this within this particular equation by finding the slope, then this way it will not be differentiable, and here you have lot of local minima, and because of this local minima you will never be able to reach the global minima. This is your global minima, right? In case of linear regression, you will reach this global minima, but in this case you will never reach, never. You'll be stuck over here, or you may get stuck over here, you may get stuck over here. Okay, so this has a local minima problem. This has a local minima problem. So how do we solve this? Now in order to solve this, okay, in order to solve this, understand, in local minima these are my points, right? I have to come over here. This is my deepest point. In this particular case, I don't have any local minima. Okay, local minima. Now, in local minima also, you'll get slope is equal to 0. So that is the reason your theta 1 will never get updated. Okay. So in order to solve this problem, you can see this diagram. In order to solve this problem, we have something called as logistic regression cost function. So I can now write my logistic regression cost function in a different way. So this researcher thought of it and basically came up with this proposal that the logistic cost function should look something like this. So the entire cost function of logistic regression, that is specifically h theta of x of I, comma y, this should be written something like this, and it should be written like this. See, here I'm just going to write cost function of j of theta 1. Let's say that I'm writing j of theta 1, j of theta 1, j of theta 1. My god, this is also not okay. So j of theta 1, what are the different output that I'll be getting? I'll be getting y is equal to 1 or y is equal to 0. So based on these two scenarios, our cost function will look something like this: minus log of h of theta of x. And I hope you all know what is h theta of x. H theta of x is nothing but h theta of x is nothing but what is h theta of x? 1 plus 1 to the power of minus theta 1 x, right? So this is what is my h theta of x, and whenever y is 0, then you basically have minus log multiplied by 1 minus h theta of x, okay, of I. Okay, so this is how you basically write your cost function in this particular scenario. Now with the help of this cost function, it is always possible, since it is getting log is basically getting used. In this scenario, you will always get a global minima. That is the reason why they have completely neglected this cost function and utilized this cost function. Now, what does this cost function basically mean? Okay, what does this cost function basically mean? I'll just try to show it to you. Two scenarios. If y is equal to 1, let's consider this is my cost function graph. Here I have h theta of x, and you know that h theta of x value will be ranging between 0 to 1 since it is a classification problem. Since it is a classification problem, so it will be ranging between 0 to 1, and this is basically of j of theta 1, which is my cost function. So if y is equal to 1, this specific equation will be used, and whenever this equation is basically used, you get a curve. See, minus log h theta of x of I, you get a curve which looks something like this. So you will get a curve which looks something like this. Okay, which you'll get a curve which looks like this. Now, what does this curve basically specify? The curve come up with two assumptions. The cost will be 0 if y is equal to 1 and h theta of x is equal to 1. That basically means when your h theta of x is 1 and the y's output is 1, that basically means you are going to assign over here 1, right? Okay, so in this particular case, you will be seeing that your cost function will be 0. Cost is 0. So here is my 0. It is meeting over here, right? If your h theta of x is equal to 1 and y is equal to 1. So this is again a convex function only, right? Uske baad, then the next point that you can probably discuss over here is with respect to y is equal to 0. If your y is 0, then what kind of curve you will be getting? You will get a different kind of curve which will look like this. H theta of x, here your value will be 0 to 1. And here you will be having a curve which looks like this when you try to plot. Okay, so when you combine these two, you'll be able to see that you are able to get a kind of gradient descent. Okay, so this will definitely help us to create a cost function. Okay, so I hope everybody is able to understand till here with respect to this, and this will definitely work. So finally, I can also write my cost function in a different way. The cost function that I will probably write over here, so this will be my j of theta 1. Okay, so I can come up with a cost function which looks like this. J of theta let me write it or change it a little bit. Cost of h of theta of x of I comma y, which we have already written, minus log of h theta of x if y is equal to 1, and then minus log 1 minus h theta of x if y is equal to 0. Now I can combine this both and probably write something like this. See, I can combine this both and I can basically write cost of h theta of x of I comma y is equal to minus y log h theta of x of I minus log one minus y, okay, 1 minus y log of 1 minus h theta of x. So this will be my final cost function. And here also you can see that if I replace y with 1, then what will remain? Only this particular value will remain, right? This value. When y is equal to 1, this thing only will come. You see over here. Replace y with 1, probably replace y with 1, and then you'll be able to see. So here I can now write if y is equal to 1, my cost function will look something like this, which is nothing but see, y is 1, then what will happen? My log of h theta of x of I will come. And this 1 minus 1 is 0, so 0 multiplied by anything will be 0. If y is equal to 0, then what will happen? My cost function will be, so when it is 0, this will minus y will become 0. 0 multiplied by 0, anything is 0. So here you will be able to see that I'll be having minus log 1 minus h theta of x of I. So this, both the condition has been proved by this cost function. Very simple. Okay. So this is my cost function. Yes, cost function and loss function with respect to the number of parameters will be almost same. So finally, if I try to write j of theta, because I have that 1 by 2m also, right? So 1 by 2m also I have. So what I am actually going to do here, you will be able to see that I can write j of theta 1 is equal to 1 by 2m summation of I is equal to 1 to m, and then write down the entire equation that you have probably written over here. Okay, so here you have minus y, or I'll just remove this minus and put it over here, and this will become plus y multiplied by, sorry, y of I multiplied by log h theta of x of I plus 1 minus y of I y log 1 minus h theta of x of I. Okay, so this becomes my entire cost function, and obviously you know what is h theta of x. H theta of x of I is nothing but 1 plus 1 e to the power of minus theta 1 multiplied by x. And finally my convergence algorithm, I have to repeat this to update theta 1, repeat until, okay, this updation, that is theta j is equal to theta j minus learning rate derivative with respect to theta j, and this will be my j of theta 1. J of theta 1. This is my repeat until convergence. So this is my cost function. This is my repeatance algorithm, and here I will be updating my entire theta 1, and this solves your problem with respect to logistic regression. Congratulations gaming with Ash. So I hope you have got an idea, guys. How was the lesson till here? See, you wanted maths. I have explained every maths over here. This is called as probabilistic. In the probabilistic point of view, how do you discuss a logistic regression? I have already explained you the entire thing with respect to equations. Okay. Simple questions may come, like how it is different from linear regression, how it is not different from linear regression. Minus is taken here, na? Minaka, so minus is taken here. Minus is taken over here, and we have to repeat this until convergence, and this is basically getting updated. So I hope everybody liked this particular video, this session. Okay. Yeah. हाँ भाई, इंटरव्यू में पूछते हैं ना, what is this all, and this much maths if you know, probably you'll also be able to understand deep learning. We are using logic function just because we got a non-convex function. During this equation you get a non-convex function, so that is the reason you are changing your cost function, guys, right? Can we say log likelihood a topic from probabilistics? Yes, this is log likelihood. Okay, now we'll do some kind of practicals. Let's do some practical now. Okay, Before that, let's complete performance metrics. This is also important. Okay. Now, I will discuss about performance metrics. Performance metrics, and this is specific to classification problem and binary classification. I'm talking. Okay. Okay, guys. Let's consider. Let's consider I have a data set which has x1, x2, and this is y. And obviously, in logistic classification, you have outputs like 0, 1, 2, sorry, 0, 1, 0, 1, 1, 0, 1. And your y hat is basically the output of the predicted model. Okay. Now, in this particular scenario, my y hat will probably be 1, 1, 0, okay, 1, 1, 1, 0. Okay. So, in this particular scenario, this is my predicted output and this is my actual output. So, can we come to some kind of conclusions wherein probably we will be able to identify what may be the accuracy of this specific model with respect to this many data points? Okay, this with respect to this many data points, because confusion matrix is all dealt with. This is called as, we will first of all have to create a confusion matrix. Now, for a binary classification problem, the confusion matrix will look like this. Okay, so here you have 1, 0, 1, 0. Let's say that this is prediction. Let's say that these are my actual value. Okay, and these are my prediction value. Okay, these both are prediction value. These are my output value. Okay, so now tell me, guys, when my actual value is 0, my predicted value is 1, does this, what does this mean? Wrong prediction, right? Okay, wrong prediction, right? So what does this basically mean? Is it wrong prediction or not? Is this wrong prediction or not? Is this wrong prediction or not? Tell me. Is this wrong prediction or correct prediction? Tell me quickly. If my actual value is 0 and my output is 1, is it wrong prediction or correct prediction? Wrong prediction. So when my actual value is 0, my predicted value is 1. So here my count will increase to 1. Okay. Let's go to the second scenario. When the actual value is 1 and my predicted value is 1, that basically means 1 and 1. So here I'm going to increase my count. Similarly, when my actual value is 0, my predicted value is 0. So that basically means when my actual value is 0, my predicted value is 0, I'm going to increase the count by 1. If I go over here 1, 1, again it is, so instead of writing 1 now, this will become 2. I'm going to increase the count. I'm going to increase the count. Okay. Similarly, I'll go over here, one more 1 is there, so I'm going to increase the count 3. Okay. Then I have 0, 1. 0, 1 basically means when my actual value is 0, I am actually getting it as 1. So I'm also going to increase this particular value as 2. Okay. And then finally I have 1 and 0 where I'm going to increase like this. Okay. Everybody clear? Now, what does this basically mean? I hope everybody is getting the same confusion matrix. Is it wrong? Wrong prediction. Okay. Now, what does this basically mean? See, with respect to this kind of predictions, whenever we are discussing, okay, this basically says, I mean, this actually says, so this is my actual values and I have 0, 1 and 0, and this is my predicted values. I also have 1 and 0. This value, when 1 and 1 are there, this is called as true positive. This value, when 0 and 0 are there, this is called as false negative. Whenever your actual value is 0 and you have predicted 1, this becomes false positive. And whenever your actual value is 1, you have predicted 0, this becomes false negative. Okay. So till here, I think we have discussed till here. Okay. Now, coming to this, I really need to find out the accuracy of this model. Guys, what you are saying wrong? What are you saying wrong? 1, 0 is 1. Let's see. 0, 1, 0, 1. Sorry, 0 and 1. 1, 0, 1 is 1 and 0, 1 is 2. 1, 1, 1, 1, 1, 1, 3. Okay. 0, 0 is 1. Perfect. 1, 0 is 1. I think everything is fine, right? Okay. Now, if I really want to find out, and this is what is called as confusion matrix. This is called as confusion matrix. Now, in this confusion matrix, if I really want to find out the accuracy of this model, it is very much simple. This middle elements that you are able to see will basically give us the right output. Okay. So this and this, if I add it up, it will give us the right output. So here I'm going to get TP plus TN divided by TP plus FP plus Fn plus Tn. So once I calculate this, okay, once I calculate this, just go ahead and calculate with respect to the values. So I have 3 plus 1 divided by 3 plus 2 plus 1 plus 1. So this is nothing but 4 by 7. What is 4 by 7? My 4 by 7 is nothing but, what is 4 by 7? 4 by 7 is nothing but 4 sevens are 35. Sorry, 7 5 is a 35. 0.7, 5.7. Sorry, 0.57. 0.57. So am I getting 57% accuracy? Yes. Okay. So I'm actually getting 57% accuracy over here with respect to the accuracy. Okay. So this is how we basically calculate with respect to basic accuracy with the help of, okay, with the help of the confusion matrix. Okay. So this is specifically called as confusion matrix. Now there are some more things that you really need to specify. Always remember, our model aim should be that we should try to reduce false positive and false negative. Okay. We should definitely try to reduce false positive and false negative. Okay. Now let's say that I want to discuss about two topics. One is, suppose in our data set I have zeros and one category, let's say in my output. If I say zeros are 900 and ones are 100, is this what kind of data this is? Is this a biased data? Is this a biased data or not? Can we say that this is basically undersampled data? It has only one kind of categories a lot. What do we say this terminology? Tell me quickly. If I have number of zeros as 900 and number of ones as 100, so what kind of data this is? This becomes an imbalanced data, very clear, right? So this become an imbalanced data set, right? So it is a biased data. Okay. Suppose if I say zeros are probably 600 and ones are probably 400. Now tell me, is this a imbalance or a normal data? This will be obviously normal data, because even though we have 600 and 400, this is not, this is, I'll just say that this is a balanced data over here. 400. So this is my balanced data. Okay. In this particular scenario, I will say that this is a balanced data, because yes, you have 100 less, but it's okay. It may not impact many of the algorithm. Now see guys, most of the algorithm that we will be probably discussing, imbalance, if we have an imbalanced data set, it will obviously affect the algorithms. Let me talk about this. Let's say that I have number of zeros as 900 and number of ones as 100. Now let's say that my model I have created, which will directly predict 0. I'll just say that all my inputs that it is probably getting with respect to this training data, it will just output 0. Now in this particular scenario, what will be my accuracy? My accuracy will be 900 divided by 1000, right? So this is nothing but 90%. So is this a good accuracy? Obviously it is a good accuracy, but this is a biased data, right? If my model is basically just outputting 0 0 0 0 0, okay, if it is outputting 0 0 0, obviously most of the answer will be zeros, but this will be a scenario like, you know, where it is just outputting one thing, then also it is able to get 90% accuracy. So you should only not be dependent on accuracy. So there are a lot of terminologies that we will basically use. One terminology that we specifically use is something called as precision. Precision. Then we'll also use recall. Okay, what is precision, what is recall? I'll write the formula over here. Okay, in precision, what do we need to focus? And then finally we will discuss about F score. Okay, so all these three we will be discussing. Till here, I hope everybody is able to understand. So we have to use different kind of parametrics, or sorry, different kind of formulas whenever you have an imbalanced data set. Okay, you can also do oversampling, but again understand, in most of the scenarios, in some of the scenarios oversampling may work, but we have to focus on the type of performance metrics that we are focusing on. Right now I'll not say F1 score, I'll say F score. The reason why I'm saying, I'll just let you know. But till here, have you understood, guys? Okay, so let's talk about recall. Recall formula is basically given by true positive divided by true positive plus false negative. Precision is given by true positive divided by true positive plus false positive. And then I will probably discuss about F score also, or we basically say F beta also. Okay, now I'll just draw this confusion matrix again, okay, which is having true positive, true negative. So let me draw it over here. So this is my ones and zeros, ones and zeros. These are my actual values and these are my predicted values. I have I have true positive, I have true negative, false positive and false negative. Now in this particular scenario, when I'm actually discussing, understand what is recall and what focus it is basically given on. So here, whenever I talk about recall, recall basically says that TP divided by TP plus Fn. So I am actually focusing on this. Okay. So what does this basically say? True recall. Out of all the actual true positives, out of all, see, remember the sentences or statements that I'm actually saying. Out of all the actual true positives, how many have been predicted correctly? That is basically mentioned by TP. Okay. Again, I'm repeating it, guys. Out of all the predicted, okay, I'll just revamp it. Just one day. Okay. So I'm basically going to discuss about recall. See, recall basically means TP divided by TP plus Fn. Okay. So again, I'm going to repeat, out of all the actual values or actual true values, how many of them has been predicted as 1? Okay, how many of them has been predicted as TP? Okay, that is true positive. Out of all these things, how many are true positive? That is what recall is basically saying, right? Now in this particular scenario over here, our main aim should be to reduce Fn. Okay, let's say that I'm taking a spam classification. Now in the case of spam classification, let's say that I get an email which has been treated as spam, but actually it is not spam. Okay, see, actually, or let me just repeat this. I'm not getting that proper sentence to say. First of all, we'll focus on the definition. Out of all the positive values, out of all the actual positive values, how many of them has been predicted as true? Okay, or out of all the positive values, how many have been predicted as positive? I can also say something like this. Okay, so I hope you're not getting confused, but just understand the scenarios what I'm talking about. Okay, because this one is my actual positive values, and how many of them has been predicted as positive? Okay, again I'm going to repeat it. Now this is the final. out of all the positive values, okay, how many of them have predicted as positive? Okay, so this is what it is basically saying, and this scenario is called as recall. In this, the false negative is basically given more priority, and our focus should be that we should try to reduce false positive. Okay, false negative, sorry, we should try to reduce this. Now let's go ahead and let's discuss about precision. In precision, what we are doing, we are basically taking out of all the predicted values, out of all the predicted positive values, how many of them are actual true or positive. Okay, this is what precision basically means. Now suppose if I consider spam classification, if I consider spam classification, if I consider spam classification, suppose this is my task. Tell me, in this particular case, should we use precision or recall? Think over it, okay? And one more use case, I'm saying that whether the person has cancer or not. In which case we have to support recall, and in which case we have to go ahead with precision. Has cancer or not? Now tell me. These two are my scenarios. These two are my scenarios, okay? Spam classification. Spam classification, should we go ahead with recall or precision? Should we go ahead with recall or precision? Just think over it, guys. Just think over it and let me know the answer. I know I require answer from everyone. In spam, what is important? Okay, guys, the recall is also called as true positive rate. True positive rate. Okay, it is also called as true positive rate. I can also say recall as sensitivity. Sensitivity. Okay. So obviously many people is thinking, and you are absolutely right. So if I go with spam classification, it should definitely go with precision. Why it should go with precision? Let's consider. Okay. If I probably get a spam mail, the main aim should be that whenever I get a spam mail, it should be identified as spam. Okay. In that specific scenario, my false positive, we should try to reduce. And in this scenario, my false positive talks about the spam classification a lot in a better way. Okay. In the case of cancer, I should definitely use recall. Let's focus on the recall formula. TP divided by TP plus FN. If a person has a cancer, if a person has a cancer, see 1, actually he has a cancer, it should be predicted as 1. Okay, it should be predicted as 1. Otherwise, if we have FN, it is basically predicting it does not have a cancer. That is really a big situation in this case. If a person does not have a cancer, and if the model predicts, okay, fine, he has a cancer, he may go and further do the test, right? And then he'll come to know whether he has a cancer or not. But this scenario is very dangerous if a person has a cancer, but he is being indicated that he does not have that cancer. So here, false negative is given more priority over here. Okay. In the case of spam classification, false positive is given more priority. Okay. So this is something important over here, and you really need to understand with respect to different problem statement. Let me give you one more example. Tomorrow, the stock market is going to crash. In this, what we need to focus on is going to crash. What we need to focus here? Should we focus on precision or should we focus on recall? Just tell me the answer. It's going to crash. Tell me, think over it again. If tomorrow the stock market is basically happening, okay, now here two things are there. Who is solving what kind of problem? See, many people will say recall or precision, but here two things are there. On whose point of view you are creating this model? Are you creating this model for the industry, or are you creating this model for the people? Right? For the people, he should definitely get identified that okay, in this particular scenario, you need to sell your stock because tomorrow's stock market is going to crash. But for companies, this is very bad. Okay, I hope everybody is able to understand. For companies, it is very, very bad. So in this particular case, sometimes we need to focus both on false positive and false negative. And again, I'm telling you, for which problem statement you are solving, that indicates. If you are solving for people, then they should be able to get the notification saying that it is going to crash. If you're probably doing it for companies, at that time your precision recall may change. But if I consider for both the scenarios, at that point of time I will definitely use something called as F score. F score, or I'll also say it as F beta. Now how is F beta formula given as? I will talk about it, and here in the F score you have three different formulas. Again, understand, not one formula, you have three different formula. The first formula I will say basically as when your beta value is 1. Okay, first of all, I'll just give a generic definition of F score or F beta. Here you are basically going to consider 1 plus beta square, precision multiplied by recall divided by beta square multiplied by precision plus recall. Okay, so here whenever your both false positive and false negative are important, we select beta as 1. So if I select beta as 1, it becomes 1 plus 4 precision multiplied by recall, then you have precision plus recall. So here, sorry, 1 plus 1, I'm extremely sorry, 1 plus 1. So this becomes 2 multiplied by precision into recall divided by precision plus recall. Okay, so here you have, this is basically called as harmonic mean. Harmonic mean, probably you have seen this kind of equation where you have written 2xy divided by x plus y. Same type, you are able to see this. This is called as harmonic mean. Here the focus is on both false positive and false negative. Let's say that your false positive is more important than false negative. At that point of time, you will try to decrease, or you will try to decrease your beta value. Let's say that I'm decreasing my beta value to 0.5. Then what will happen? 1 plus 0.5 whole square, and then you have P multiplied by R, precision in recall, and here also you have 0.25 P plus R, right? Now in this particular scenario, I am decreasing my beta. Decreasing the beta basically means that you are providing more importance to false positive than false negative. Okay, and finally you'll be able to see that if I consider beta value as, let me just say my notes, if I consider beta value as 2, that basically means you are giving more importance to false negative than false positive. Okay, so with this specific case, you can come up to a conclusion what value you basically want to use. Now whenever I use beta is equal to 1, it becomes F1 score. Okay, if I use beta as 0.5, then this basically becomes F0.5 score, and this becomes your F2 score. Okay, I hope everybody is able to understand, guys. Clear? Hit like, everyone. How many of you have heard that I have also now started uploading videos in Hindi? So my request is that please make sure that you subscribe the channel of Hindi also, because there also I'm coming up with a lot of videos. Okay. So how was the overall class, guys? So I have already pinned the link, guys. Please make sure that you subscribe. So based on which is important, okay, which is important, whether your precision or false positive or false negative is important, you can consider those things. F score will have different values. If you are using beta is equal to 1, that basically means you are giving importance to both precision and recall. If your false positive is more important, then at that point of time you reduce your beta value. If false negative is greater than false positive, then your beta value is increasing. Beta is a deciding parameter to decide your F1 score or F2 score or F point score. Okay. So my request, guys, everybody subscribe to Krishna Hindi channel. There I'll also be uploading a lot of Hindi videos. And already for those people, did you receive these materials? It is present in the course link that I have given down. It is community session, and please like the video so that we complete 1000 likes. And I hope you are able to understand this video very much nicely. Okay. Now it's all your learning, guys. See, definitely 1.5 hour, 2 hour is very less to explain everything. But do you see the type of maths that I'm using? If you go this much prepared, no one will be able to stop you to basically get jobs. So that is what is my focus point, that everybody should be perfect in maths. Okay. Now, whatever other things you have, do Google, search it, try to find out. And tomorrow, I think it's already time, it's 8:47. Okay. So I will take the coding part tomorrow, first session. Till then, please make sure that you make 1000 likes, at least 1000 likes. 992 likes are there, more 8. And yes, start sharing this in LinkedIn platform, in Twitter. Try to show people, try to write all these equations, what you are doing, and try to contribute for other learning, so that many people will again join in tomorrow's session also. Okay. Okay, guys. So this was it from my side. Have a great day ahead. Thank you, one doll. Keep on working, keep on learning. And anytime, if you are good in this much things, see how much effort I have actually put to teach you, and I'm also putting daily effort this much, right? Whatever I have uploaded from past 2 years, I'm just being able to teach you in 7 days. Okay. So please take care, and yes, keep on rocking. I'll see you in tomorrow's session. Have a great day. And tomorrow we'll be learning. First of all, we'll start with coding, and then we'll learn new algorithms. Okay.